Good day, everyone. Today I'm excited to share insights into my latest study on credit card default prediction, a crucial aspect of my evolving financial landscape. As credit cards become increasingly integral to daily transactions, the risk of defaults, where cardholders fail to meet their debt obligations, poses a significant challenge, affecting not only individual credit records but also the broader financial system. At the heart of this challenge is predicting whether a cardholder will default in the near future, based on a variety of factors like personal characteristics, transaction history, and repayment behavior. The complexity of this task stems from the diverse behavior patterns among cardholders, making accurate prediction a difficult yet essential task. My research zeroes in on how machine learning can revolutionize credit card default prediction. We focus on extracting key features from expensive datasets to reflect credit standing more accurately, developing robust predictive models to identify underlying default patterns, and translating these predictions into effective risk management strategies for financial institutions. By enhancing the precision of default predictions, we aim to empower financial institutions to manage risks more effectively and help cardholders navigate their finance better, avoiding the pitfalls of debt. Traditional methods have their limitations, but with advanced machine learning techniques, we can dive deeper into data, offering more insights into default risks. Next, let's dive into the world of credit card default prediction, exploring its background and the role of information technology and machine learning in reshaping this domain. My journey begins with the concept of information asymmetry in financial transactions, a scenario where banks and lenders often find themselves at a disadvantage due to the lack of transparent information about borrowers' repayment motivations and capabilities. Pioneering research by Stiglitz and Weiss highlights how this asymmetry leads to adverse selection and the moral hazard, worsens the risk of defaults. In essence, banks end up favoring higher interest rates, which might exclude the most creditworthy borrowers, skewing the market towards higher risk. Enter the realm of data science and machine learning, revolutionizing my approach to the challenge. With advanced computational power and an abundance of data, machine learning algorithms like random forest and XGBoost have become game changers. They excel in dissecting complex data, revealing patterns in cardholders' behaviors that traditional methods might miss. But the technological landscape is vast. I compare traditional credit assessment methods, which often rely on limited financial data, with the dynamics and the comprehensive analysis provided by machine learning models. These models can process diverse data types, adapting to changing economic conditions and consumer behaviors, although not without challenges in data privacy and algorithm bias. Deep learning, a subset of machine learning with multi-layered neural networks, further amplifies my capabilities. It excels at unraveling the complex non-linear relationships in financial data, offering insights into cardholders' behavior patterns. This technology continually evolves, becoming more accurate as it processes new data. Then I will share with you the execution phase of my project on predicting credit card defaults using machine learning techniques in Python. This project is not only about leveraging technology but also about gaining deeper insights into financial behaviors. We began with data preparation and pre-processing using Python libraries like NumPy, Pandas, Matplotlib, and Seaborn. We managed data manipulations, visualization, and model building efficiently. My study is anchored in a dataset from a major bank in Taiwan, China, consisting of 30,000 credit card holders, including over 6,000 defaults. My model has 24 variables, including customer-specific attributes like gender, age, and financial particulars. These were not just isolated characteristics, but connect with each other, requiring comprehensive feature engineering. This involved creating new features such as credit card usage rates, payment behaviors, and bill amounts to describe potential default attributes more effectively. In the model development phase, I used a heat map visualization of the correlation coefficient matrix to understand the relationships between variables. This was crucial for feature selections, which we streamlined use Pearson correlation coefficients and a random forest model to identify the most impactful features. I then embarked on building the actual predictive model. 5 machine learning models were selected: KNN, decision trees, SVM, random forest, and XGBoost, alongside a deep learning model, an artificial neural network. Each model was implemented and evaluated for its performance. A critical step was splitting my dataset into training and test sets, ensuring data independence of results. I optimized each model using grid search and cross-validation strategies, evaluating them based on accuracy, precision, recall, and other relevant metrics. For instance, in my KNN model, I explored various parameter combinations to optimize performance. Similarly, for decision trees and SVM, I conducted thorough parameter tuning. In the case of random forest and XGBoost, I identified key features impacting the model's predictions and optimized them for better accuracy and efficiency. Lastly, the implementation of an artificial neural network model trained with binary cross-entropy, loss function, and the Adam optimizer showcased the model's practical application and predictive capabilities. In this part, I will share a critical evaluation of my project on predicting credit card defaults using various machine learning models. This evaluation is essential to understand how each model performs and to identify areas for further research and improvement. My first step was to analyze the feature importance in predicting credit card defaults. The most influential feature was PayZero, the most recent month's payment status, indicating that recent payment behavior is a strong predictor of default risk. Other significant factors included the usage rate, age, average payment amount, and the credit limits, each contributing uniquely to the prediction. In my machine learning experiments, I evaluated 5 models: random forest, XGBoost, SVM, KNN, and the decision tree. I assessed them based on accuracy, precision, recall, F1 score, and ROC metrics. Random forest and XGBoost emerged as top performers with accuracy scores above 82%. They also led in precision, indicating a lower rate of false positives. However, when it comes to recall, measuring the model's ability to identify true positives, the numbers were relatively lower, suggesting an area of improvement. When comparing this result to the AM model, I observed that while the AM model had reasonable accuracy, it lagged behind, especially in the ROC metric. This highlighted the potential of techniques like random forest and XGBoost in credit card default prediction. The varied performance of these models can be attributed to their characteristics, the dataset's nature, feature engineering practices, and hyperparameter tuning. For instance, a model requires large amounts of data and careful tuning of hyperparameters, which may have limited its performance in my study. Looking at the broader picture, the research revealed several limitations such as data quality, model-specific constraints, and the generalizability of the models. For example, the AM model's black box nature poses challenges in interpretability, a crucial aspect in financial applications. In conclusion, our study on credit card default prediction represents a significant step in addressing a vital financial challenge. I delved into the complexness of the credit card industry and its impact on the economy, focusing on the crucial issue of credit card defaults. Utilizing the comprehensive dataset from the UCI Machine Learning repository, I explored a range of advanced machine learning algorithms, including traditional models like random forest and XGBoost, and deep learning techniques such as artificial neural networks. My approach was grounded in understanding the phenomenon of information asymmetry in credit markets, as highlighted by economics, Stiglitz, and Weiss. I recognize that this asymmetry often leads to adverse selection and moral hazards, contributing significantly to default risk. To combat these challenges, I employed machine learning to uncover hidden patterns and trends in the data, thereby offering more accurate predictions of default risk. Thank you for watching.